Okay, hope it's going well, class. I want to go over some of the code that we've written for chapter 5, dealing with probability. So here is the code. You probably have most of it from class. But let's go over it. You see that I've cleared the plots and my environment, which might be a good habit for us to go get into moving forward. So let's go here first. We have n is equal to 10,000. In this case, we're going to look at a randomness from 0, 1. And there's a couple of different ways to do this this is just one particular one. And I stress this because in the way the code is written, there's a bit of a limitation to apply it for when there's, for instance, more than one option, more than the 0, 1 binary option. Anyway, let's get into it. First, you have n, we're setting it to 10,000. That's because we are going to do a coin flip simulation. 0 is tails, heads is 1. Now in this line of code, line 5, we're going to make another object called x, right? X, make an object using that sign. And that's going to be, we're going to sample from 0 to 1, 10,000 times. We are going to replace because we need to, right? Because if you don't replace, you flip 1 heads, then you don't pick heads again, you pick 1 tails, then you don't pick tails again, and you have 98,900, I'm sorry, 99,998 trials in which you don't have a heads or tails, so you have to replace. So replace is equal to t, or we can make it as easier as true. And then here's the probability that you could either get a 0 or 1. So in this case, there's a 50-50 chance that you'll get a 0 or 1, replicating, obviously, a coin flip. So if we run that and we look at x, here are all the values. And again, that goes on for, I guess I said 99,000, but we're only doing 10,000, not 100,000, though in R. You could easily, anyway, here are all 10,000, or I'm sorry, there's omitted 9,000. Here's 1,000 of the generated sample. In this one, look at this line of code. We're making an object called S, which is equal to the cumulative summation. So you can see that on line 1 of the 0, 1, it's 0, 1, and then a bunch of zeros, and then a 1, a few zeros, a 1, a few zeros. If we go to S, what's happening is it's saying 0. Now the second trial, there was only, it was a 1. And then the third trial was a 0. The fourth trial was a 0. The fifth trial was a 0. The sixth trial was a 0. All the way to, like, I don't know, this might be the 10th trial. There was another 1. And then there was 0, 0, 0. And then there was another 1, 0, 0, 0, 0, 0. And then there was another 1. And eventually, well, you'll see what happens here. But all that's happening in this next line of code is we're averaging that number by the number of trials. That's what this little bit of code is doing. It's saying the first trial, you're going to divide by 1. So what was the coin flip if you summated it? And I think that the S at that point would be 0. So you'd have 0 divided by, in this case, 1, because it's the first trial. So it's going to equal 0, of course. Let's look it over. Yeah, 0. And then the next one was a 1. So that became 1 over trial 2. So 0.5. Then the next one, it was a tails. So it was a 0. So that became still 2, now divided by 3. This is very easy to see in this object, which is more like a table. We've used this line of code that says cbind, which stands for column bind, in which we're binding the sample, the cumulative summation, and the average. So let's look this over. X was 0, tails. So S was 0, summation. And so it was 1 over trial 1. I'm sorry, 0 over trial 1. So 1, which is 0. By trial, and this is a particularly interesting sample because there's so many zeros on the front end. By trial 25, for instance, trial 25, we got a 0, but by 25 coin flips, we had 7 heads. Okay, so it's 7 divided by 25, which is 0.28, which I believe I can check it out, but I guess that checks out. Yeah, there you go. So conversely, by, let's just say, trial 175, it itself was a tails, but we had 84 heads up until then. So we do 84 divided by 0.45. So yeah, 84 divided by 175, 0.48. I'm sorry about that. So that's one of the reasons why this is sort of a limited way to do this random process, because it's based on the summation equal to 1 to tell us the outcomes of this process. Still useful because there are plenty of random distributions that are binary, but just know that you will want to use the next bit of code if you're dealing with more than 2 outcomes. Okay, so here's where we can get, oops, what happened here? Okay. Here's where we can get something kind of cool, which is a plot of this. So I have this table. It's really helpful. Obviously, it helps us just kind of digest some of the data, but I want to get back to this object over here, which is in essence the probability that you have a 1 or a 0. So in this case, I can plot this number or this list of numbers. If I just did this, plot R AVG, you'll get, you might expect this, excuse me, given our previous work with R, but you're getting a lot of points, which is not ideal. So I do a type L, which means it's going to give us a line. Let me run this. Oops, sorry, actually run. I made a prettier one. You run that, and then run that, and then I'll tell you what's going on. It's kind of interesting. Again, I'm plotting that number. It's a line. The main title is probability of random selection. Let me actually add this. Remember, I always forget this one or this one. Yeah, there you go. Make it a 2-line title. And I made this line dark red. I labeled the X and Y axis. You can see trials, how many coin flips, and then the probability of getting, it's really getting 1, but one gives you the other through the complement rule. And then I can add this, which is the theoretical probability distribution. So we know it was 0.5. Remember early on, there were so many zeros. That looks like it really, in this sample source, incorrectly showed, obviously, because you do it the more times you get closer to the true probability, that is a really low likelihood. So if you had only done, for instance, 25 coin flips, then if someone was suspecting if that was a fair coin, they might say the 25th trial, this does seem like, it's a third of the time. You, by the way, can't see the bottom of this because I changed the Y limits. I can change it again just for the sake of demonstration. But actually looks like this probability gets straight to 0. And then obviously jumps back up. So I can, there you go. But I put the Y limits on there because it looks a little bit nicer, especially because if I put 0, then it looks like higher, and so it's a bit of a visual thing. If I put 0, 1, well, I guess in this case it looks fine, but I'm gonna zoom in, show a little bit of variation, and then this is how I add the lines. Okay, and obviously I went through some of the components of this snippet of code, but this let's just briefly discuss. So you have a line that starts at x0 and goes to n, which we've discussed is 10,000. Okay, so that's where it ends right here. And in terms of the y starting point, it starts at 0.5, it ends at 0.5. So a pretty easy line of code. I could change this to say, go to 5,000 and go from 0 to 0.5. And I could also change the color to yellow. And that's what I'm going to get. Which is obviously there's no point in doing that. I just want to show the different elements of the code. So let's go back to this. Okay, so there is how to use R to model a random outcomes between two outcomes. Sorry. Now let's go to the next bit of code. This one works off of the example in the textbook about racer cards and the amount of trials or doing multiple trials to see how many boxes of cereal you would need to buy to get all 5 of these racers. Okay, this code gets a little complex, and it's where we step into the while loop and for loop territory. This is automation, which is kind of cool for me. Maybe it's not cool for you. Here, actually, I'm going to reset everything again just because I don't have clean slate. Okay, so here I'm making a new object called all racer cards, and it's equal to C, which is making C, by the way, stands for concatenation, I think. Making a list of DP, which was Danica Patrick, JJ, which is Jimmy Johnson, and then I made these other 3 up, though. Hopefully there's at least, one person with all of these initials in NASCAR, which was the context of the problem. Anyway, so here I made this new object. Oh, there you go. And here it goes. It's 5 elements long. 5 elements long. Elements a good word because it comes up later. So the next one I'm making is called one racer cards. And actually, this is a very interesting object because it's null. It's nothing. It's going to be dynamic. We're going to add to one racer cards. Okay. So we have 2 different types of loops, while loop and for loops. Let me go over the while loop, and obviously went over this in class quite a bit. So I trust that between this video and class time, you get this. If you don't, please come and speak with me. So what's happening with this while loop is that it's saying, while this condition is, in this case, false, continue to do it until it becomes true and then stop. Okay, so and vice versa, I could set a while loop that says, hey, do this thing as long as this is true, but once it's false, stop it. And I know that sounds a bit abstract, but I think it will make sense in the context of this example, if this is the first time you're hearing it, of course. So what you think about when you have this example with the race car drivers and the cereal boxes is you're told that there's an equal probability of getting all 5 of those race car driver cards in each cereal box. So you say, okay, like I'm gonna open one box, I have this card, open another box, I have this card, and you're gonna do that until you have all 5 cards. And you're going to assess that to see how many boxes it would take if they're all truly randomly distributed. Obviously, you know enough to say that it's not guaranteed that you have 5 boxes, 5 for 5, you're going to get every single different one. But how many would you need to buy to get all 5, given the probability of receiving one of them? So there are the 5. And now, given that background of the example, let's talk about the code. This is a new aspect of the code for you, I imagine, and I'm going to, hopefully it's helpful when I go over to you again within the context of the example. while all of the elements in all racer cards are false, are not in one racer cards, do this thing. So what I set this up for, one racer cards, is a list of all the cards that I get. And I'm going to stop when I have all 5 of these elements, all elements of all racer cards in one racer cards. So for instance, if I get, well, let me step forward a second more. Then you have the box card. This is going to happen every time you open a box of cereal. It's going to pick a random sample. It's going to pick one of the all racer cards at random, and you're going to say, this is the card I got when opening this box. Okay, so let's see what happens. I'm going to run that line of code, and you see that DJ, I got the DJ card. Cool. What I'm going to do now here is append it. I'm going to add DJ to all of my race cards. Okay, let's see how that looks. DJ. Now I'm going to open another box card. It's going to sample from all racer cards. It's going to sample one of them. I'm going to look at it. Oh, this time I got JJ. Okay, I'm going to append JJ to my list of the race cards that I won. And now if I look at one racer cards, I have DJ and JJ. Now, are all of the elements of all racer cards, all 5 of these, in one racer cards? No, right? There's 5 elements here and I only have 2 cards. If I run this maybe 20 times, maybe I will get enough. Let's see if I look at it now. DJ, JJ, PJ. Nope, I still don't have CC, or I still don't have DP. So it would continue to go. That's what the while loop is doing, is saying, while not all of the elements are in your one racer cards object, keep running this. So let's look at it and see what happens. I'm going to clear that again. So start off with one racer cards as null. Oops, sorry. Here we go. In this case, one racer cards has 14 elements. DJ, it took a while for you to get to. So now I have that trial took 14 boxes. Let's run it again. Oh, sorry. You have to reset every single time. So make sure you run this line of code, the one racer cards, if you're replicating with me. That time it took 7 tries. That's pretty good, right? So it looks like I got, let's look at it, PJ, CC, JJ, DJ, and then Danica Patrick again. Let's try it one more time. That 8, let's look for a long one. 20, okay. Let's look. So it looks like it took a while to get your CC. You had a lot of PJs, okay? Now, again, this was just a trial. And so the next thing we're going to do is reformat this into a simulation, okay? Because right now I'm just going through and running this over and over again, 9, 30, 18, 9, okay? But I want to automate this. So actually what I did was I copied this whole block of code from 18 to 25, and I pasted it between 30 and 34, okay? So that's all within now a for loop. A while loop, remember, goes until the condition is true or false, or not true or not false. A for loop will go as many times as you tell it. And that's what I'm going to tell the code to do, is I'm going to say 1,000 times I want you to run the simulation. The only thing I'm adding in the for loop, right outside the for loop, I put this object, again, a null object, an empty object called number of boxes. And that's what this number was. That's what the 10 and the 5, 24, 18, 30, those were all how many boxes it took to get. And so I'm going to 1,000 times over run this and add that number. That's why you see the append here. I'm appending this new object, number of boxes, by the, you see what it said, length of one racer card. So let me just go over that quickly. So again, this is one racer cards. It has 10 objects, so that's the length of one racer cards. That's why it took 10 boxes that time. So here I made a new object called number of boxes that's null, and for 1,000 times over, it's going to run that simulation and add that final number, the length of the one racer cards. We run that. Okay, see, it takes a little bit longer because it's running it 1,000 times. Let's look at number of boxes. Okay, so and this might be, what am I going to glean from that? You know, but if I make it a histogram, okay, it looks like several times it happened with fewer than 10 boxes. Mostly fewer than 20 boxes for sure. But it looks like it even happened one time out of 40. I can run this again, and we can expect that generally the distributions are going to look relatively similar. It looks like this one had a few less outliers. It didn't have 40, so we're getting what I think is a little bit nicer of a histogram. It will look certainly more stagnant if I do this 10,000 times, which takes a little bit longer. But here, if you do it 10,000 times, it looks like you do have more consistent variability, which explains why we have some real outliers, sometimes taking more than 50 boxes, which is like $200 worth of cereal. Now, I'm going to go over this in class today, so this next quick part might be a little novel to you, but it's actually working back from code that we learned before. Excuse me. Remember the for loop, and also look at the grammar here. You see I in 1 to 10,000. So for 10,000 times, start at 1, go 10,000 times, add the number of boxes it takes. Again, for loop different than while loop. I'm creating this object. That's what I'm making the histogram of. Okay, and this object looks like this. Okay, I can use the table function, which again you might remember, and count how many times it took. For instance, 5 boxes, 6 boxes, et cetera, et cetera. So then I can use, again, some snippets of code that might look familiar from chapter 1. I want to take the table. I'm going to make it actually a proportional table. And then I'm going to make that a bar plot. Let's see what that looks like. Okay. So let's actually zoom here. Sorry. It gets a little sloppy. I'm going to change one line of code real quick. You might recall this. See if this is any cleaner. Yeah. So 0.0, so 5% of the time it took 5 boxes. Looks like the most was 8 boxes. Maybe that's like 12% or something like that. And of course, these larger numbers, they're actually a very small probability, but good to know that it could take this much. Obviously, this isn't a normal distribution, but you can see its utility. Most of the time, for instance, it's going to take less than 20 boxes. Actually, a good portion of the time, less than, for instance, 12, 11 boxes. So here, again, we use the bar plot function, and we made a proportional table from the table of the number of boxes. I'll go over this in class, but hopefully this whole video is helpful to show how we're using especially random sampling and some useful context to understand this aspects of the code in R. Okay, with that, I hope you're the best the next time you open R and try and play with this yourself.